I had to get up at 5 o'clock in Seattle this morning to fly down here, and when I arrived, I saw a little news item came over that both Jeff Bingaman and Stephen Chu were returning to Stanford, and I thought that was really impressive. But I also am returning to Stanford. I was born on the campus, so 65 years ago. My parents lived in Redwood City at the time, and I didn't ever visit the campus until some years ago. When I was on a morning run when I was down here on business, and I stopped and I called my wife, who is a graduate of Stanford Law School, and said, "This is ridiculous. You know, I went to school in cold, grimy New England, and you went to school at Destination Resort." And she said, "Well, school is supposed to prepare you for life, and life is a destination resort." She also said Stanford was not perfect. You had to drive too far if you wanted to go surfing. I am really delighted to get to come here today. Don't have enough time to do as much in depth as I would like, but I thought what I would try to do is to tell you a little bit about what we've gone through to try to develop a really large scale electric power plant that captures its carbon, 2.5 million tons of carbon a year, and more than 90% of the carbon in the power supply. The project I'll talk about today is our Texas project. It's called the Texas Clean Energy Project. And I did not bring a PowerPoint. If you want one, I'm happy to send one. Sally can give it to you. But we have a website for the project, which is called TexasCleanEnergyProject.com. And there's also, of course, a website for our company, which is SummitPower.com. So there's plenty of information out there about it. A sort of the basic premise of carbon capture is that you have to have a sink. There's no carbon capture project without a sink. And Sally and her colleagues and others have done a really good job working on sinks. But also, by the same token, there's no carbon capture project without capture. And what's going on around the world on carbon capture is lots and lots of small projects, quite small projects, experimental projects, but not massive tonnages being captured. And if you accept for a moment, and just for purposes of today, until we get to questions anyway, let's accept that it's important that you should, in the end, do carbon capture and sequestration on a really large scale. You have to have plants that are actually capturing on a really large scale, which is what we set out to do. And if you think there's some urgency to this, which I do, then you want to start moving along fast. You don't want it to all be research. You want to actually go commercialize it, get it moving, start putting carbon in the ground. The commercial realities, however, for developing one of these projects in the power sector, and I should mention, you know, we do climate-friendly power plants. It used to be that we were the guys doing the natural gas plants when other people were doing coal. We've never done any coal. We started doing wind and solar, which we do. We have some big project in California right now, a big solar project. We have plenty of wind that we sell down here. But we started on carbon capture and sequestration back in about 2001. And we wanted to do it on a commercial basis. And we knew that people were saying it couldn't be done on a commercial basis. Because the environment included, there's no renewable portfolio standards for low carbon projects. Except in 1 or 2 states. Michigan has one, but basically there are no standards that require utilities to buy low carbon power as opposed to renewables. As you all know, there's no price on carbon, really, California being an exception, but in general there's no price on carbon. And so, you know, what's involved in making a plant commercial and being able to finance it and get it built? We had heard so many industry presentations where people say it can't be done. They would get up and wring their hands and say it can't be done, it can't be done. Our chairman of our company, Don Hodel, who was the Secretary of Energy and Secretary of Interior for Ronald Reagan, is a very conservative Republican, and you can bet he is not a real believer in the climate hypothesis. But he just basically said, this is kind of un-American to say we can't do this. Why don't we do it? And then that'll be over with, and then people can start talking about other things than the fact that you can't do it. And that's sort of how we got started. So in 2001, the California energy crisis, we'd been building gas-fired power plants like mad, and all of a sudden, as you recall, it just came to a screeching halt. And I got on the plane, went back to Boston to see the Clean Air Task Force, and sat down with them and said, look, mathematically, it looks like we're going to have to do something with coal. And we, Summit Power Group, have a firm principle, which is never do a project environmentalists will oppose. And it's not because you can't sometimes win, it's because there are other projects to do, and if you only make your money by doing projects that are successfully built, you don't want to mess around with ones that people will oppose. So I said, so how would you do a coal plant that environmentalists would support, or at least not oppose? And so They introduced me to the concept of IGCC, which I thought was a specialized United Nations commission, but it turns out it's an integrated gasification combined cycle. Stupid name and acronym for a type of power plant with gasification. And also to carbon capture and sequestration, which is something I'd never heard about before. And when we really started to understand this technology and what was involved, we went to see Siemens. Siemens is a company that we have a lot of good, very good relationship with over many, many years, and sat down with Siemens and tried to explain to them why we felt as Summit that they had a bigger stake in gasification than General Electric as their competitor. And one of the reasons is because Siemens really likes to build combustion turbines, and if you could gasify coal, then you have a clean fuel for the combustion turbine, which is really high hydrogen. And Siemens was very interested in doing high hydrogen turbines. So we went to see them in the early first decade of this century. And at the time, they didn't own any gasification technology. But they had a good relationship with ConocoPhillips, which had a nice gasification technology called e-gas. So like most of these technologies, they weren't developed for the power sector. They were developed for the refining sector and for the chemical sector. But we decided to try to put together a plant using the ConocoPhillips gasification technology with Siemens high hydrogen turbine. So let me stop for a minute. Probably most of you know this technology or the chemistry better than I, but just to make sure that everyone does. When you gasify coal, which is something people have been doing in the United States and around the world since the 19th century, they just didn't do it very cleanly for a really long time. But when you gasify it, you're taking a solid fuel, which is a dense concentration of atoms and molecules that are really valuable, and you don't burn it. You use a thermochemical reaction in a gasifier. You're very careful not to burn it, to break it down into its constituent molecules. And the critical thing you get out of this, which is called syngas or synthesis gas that comes out of the gasifier, is actually a combination of carbon monoxide, CO, and H2, a hydrogen gas. And of course, there's an extremely high ratio of carbon to hydrogen if you're using coal or pet coke or some other solid fuel, a solid feedstock, I should say. They're none of them fuels, they're just feedstocks. But you can use existing technology to remove that CO. And the way you remove the CO is that you basically put it in a big room with a lot of steam and a little chemical catalyst. And the steam being H2O, with the chemical reaction, the O2 comes off, and you're able to get the O to join up with the CO2, the CO to become CO2, and the H2 just goes and joins its colleague H2s. So when you come out of this, what's called, these are all bad names, the water gas shift reactor. When it comes out of the water gas shift reactor, now instead of a stream of CO and H2 with a huge amount of CO and a small amount of H2, now you have a gigantic amount of CO2 and a gigantic amount of H2 and a little bit of CO. And you can pull the CO2 off using conventional technology so that all that's going into the combustion turbine is the high hydrogen fuel with a little bit of carbon in it. And that carbon does end up as CO2, but it's a very small amount. So just our Texas plant will have 195 pounds of CO2 per megawatt hour. A natural gas-fired power plant of the most efficient design operating in perfect conditions is about 900 pounds a megawatt hour, and a coal burning plant is about 2,200. So you have some carbon left over, but very little. And the technology exists to do all this. There's no new technology involved. It's been done in various ways in the gas and chemical industry, refining industry for a long time, but not in the power sector. So we set out to try to find a site, and we looked in a lot of places. We had geologists who said you should put it in mafic rock up in the Pacific Northwest. And we had people saying, no, you should put it in oil fields in Wyoming. And we had all these different places. So we looked all around to find a good site. And we started in Oregon, we went to Montana, and we ended up in Texas. Why did we choose gasification? Because there are other methods of capturing carbon. What we really found appealing about gasification is that nothing gets burned until everything's cleaned up. So with gasification, you take the solid fuel or feedstock, the coal, you break it down into all its constituent elements, but you never burn anything that has mercury in it. You never burn anything that has sulfur in it. You don't put that stuff up there and then try to figure out how you're going to pull it out. You drop it all out of the process before you get anything that burns. So the only thing that ever gets burned when you do have a gasifier in the power sector is this high hydrogen, low carbon syngas. And one hopes there'll be ultimately all hydrogen, right? But for the moment, really high hydrogen, low carbon. That's why we chose it. The other reason is, of course, you have the chemical building blocks. You can make any product you want out of that syngas. Whereas if you do post-combustion capture, like you're trying to go to an existing plant and sort of slap something on that'll enable you to capture the carbon, the only thing you're going to be able to do is just produce electric power and capture carbon. You can't make anything else because you have no other chemicals that you're capturing. So when we started, there weren't any available incentives at all for the project, and there weren't any specific precedents. Sometimes I tell myself it's amazing. We've spent 10 years moving society's technology on this front forward about half an inch, because you're probably aware that there are two gasification plants that do produce electric power in the United States, one in Florida and one up on Lake Erie, but they don't capture their carbon. On the other hand, there's a great gasification plant up in the Dakotas called Dakota Gasification, and it gasifies coal and makes everything else in the world and captures its carbon. The carbon is sent up to Saskatchewan, but they don't produce electric power. So we said, okay, how about we gasify the stuff, capture the carbon, and produce electric power? That seems like a pretty small increment of advance, and yet it's been awfully difficult. When we started, the environmental community that we were working with, the environmental groups, which were the Clean Air Task Force, Environmental Defense, and Natural Resources Defense Council, their view at the time was, well, let's build the first 10 plants and have them be what was called carbon capture ready. So since you didn't have a sink, just show that you can capture huge amounts of carbon. Just do catch and release for the first 10 plants, and then you'll get the technology established and so forth. And David Hawkins of NRDC put an end to that. He went to the Gasification Technologies Council big meeting in San Francisco one year, and he got up and he said, in front of the crowd, he said, "Carbon capture ready. Carbon capture ready. What does that mean? I have a garage that's Ferrari ready." And, and the minute he said it, he moved the goalpost right away. And as I've had the pleasure of telling him in public many times, thank God he did, because it turned out technologically the whole idea of making it carbon capture ready, and then you were going to come back later and retrofit it with a shift reactor, water gas shift reactor, all that stuff, was always a stupid idea. It was crazy, because these plants are very, very carefully balanced thermally and mechanically and everything else. You're not going to have a sort of a shadow plant that's built into the existing plant and then come back and change it. It's just very, very hard to do. So fortunately, we got pushed in the position of actually capturing our carbon, which helped us design plants that made sense. We started in Montana with an actual project we designed. We started there because we had a client who wanted one built at sort of industrial scale. A very, very large silicon manufacturer, the largest silicon manufacturer for solar and for computer screens. And they wanted to have a decarbonized power supply, but they wanted their own power supply. So we went to work on this, and it was something that would have been economical if the Waxman-Markey climate legislation had passed, because the climate legislation had very large financial incentives for capturing the CO2 and getting it geologically sequestered. So with that incentive, it made economic sense. But it only made economic sense with that because you had to build a 300-mile pipeline down to Wyoming in order to find a place to put the CO2. And Waxman-Markey would have paid for that, but without Waxman-Markey, there was no way to pay for it. However, we did have years of work on the actual design of the plant with the Siemens with the Siemens high hydrogen combustion turbine, which Siemens had spent the money to develop. It's not the same as running a turbine on natural gas. There's some modifications you have to make because the syngas doesn't have the carbon, and it has mostly hydrogen, which is very, very light. And there are lots of technical issues that are introduced by trying to burn hydrogen in a turbine that require modification of the turbine. But Siemens also didn't have a gasification technology at the time. And as I mentioned, we were going to use ConocoPhillips. And Siemens signed the joint venture papers with ConocoPhillips and Fluor, who was the engineering company. But Fluor and ConocoPhillips were having a dispute in some other part of the world. And so the two of them never signed. And about that time, the Clean Air Task Force came to see us again and said, you know, there's a technology over in Germany called the GSP, gasification technology, and you should have Siemens take a look at it. And So the people from the Electric Power Research Institute said the same thing, and so we did. We said to Siemens, why don't you go take a look at that? And they ended up acquiring it in 2007. They bought this whole technology, and it turned out to be a great day because it's just an amazingly good gasification technology. Very, very robust, reliable, very, very efficient. In a way, it's too bad for the history of gasification that General Electric didn't buy it, because General Electric's really the industry leader in our sector, and they bought the Chevron Texaco technology instead, which is technology is good, sturdy workhorse technology, but didn't have the potential, the upside potential that the Siemens one did. And there we were, busy designing that project, and a few things happened in pretty quick succession. The chronology is a little mixed up here, but first of all, 2008, the financial crisis at the end of the year meant that the size plant we planned a half-size plant in Montana, a full-size plant in Texas. It meant that there was no way you were going to do a full-size plant. There weren't enough banks in the world to give you the debt that you needed to project finance a project with that many billions of dollars. And so we had to go for the industrial size plant and say, let's find a way to make that economical. Up until that time, everybody had thought that the minimum scale for a gasification plant was so large that you needed at least a 600 megawatt plant for it to make any sense. And we found that actually, fortunately, that was not true. And we were able to take all the work we'd done in Montana, move it to Texas, and have a 400 megawatt plant and have the economics be quite good. By this point, the federal government had come up with one powerful incentive, which was federal loan guarantees. And probably heard about those in California. And so we thought, well, okay, there's a financial crisis, but maybe we can use a federal loan guarantee. And so we planned to do a federal loan guarantee. We filled out the application, which was a huge process in end of 2008. And the day before we were supposed to file it, our equity partner in the project in Texas said, we can't do this. We can't sign this because by signing it, we're required to turn over all our financial information to the Department of Energy. And it'll certainly leak from that and from DOE, and we just can't do it. And you know enough about Texans to know that there's probably some stuff that they don't want to have leak. So we didn't apply for the federal loan guarantee. We thought, well, so some other projects will get them, and we'll wait till the second round. And indeed, other projects did get them. None of those projects has been built, but they did get them. And we decided we would go along and see if we could get some help from the state of Texas. So we spent the first part of 2009 working with the Texas legislature to get some same incentives that Texas had offered previously to the FutureGen project. You probably have all heard about FutureGen. FutureGen was itself a gasification project that was a DOE-funded project that was designed to do many of the things that our plant will now do. There was an alliance of many industries and the DOE to find a site, and the finalist sites were in Texas and in Illinois. And we had been looking around Texas. Texas looked at 12 sites, and they had 2 finalists. And so we were looking at the other 10 while FutureGen was still considering the first 2. And then one day late in 2008, FutureGen moved from Texas to Illinois. They decided to pick the Illinois site. And the next day, the people at the Texas site called us up and said, would you come out here? And we flew out there. And this is a site near Odessa, Texas. It's an absolutely amazing site. It's not perfect, but it's an extremely good site for a first-of-a-kind plant like this. And so we were happy to get that site. The state of Texas was happy to ultimately enact the incentives, which were basically tax incentives. And interestingly enough, the key tax incentives are not for the plant. The key tax incentives are for oil producers who use CO2 from the plant, who agree to inject and monitor their injections and so forth in a manner that will meet the Texas standard. This is probably surprising in California, but Texas is by far the most advanced state when it comes to carbon capture and sequestration in terms of their legal regime and their incentives. If you want to inject CO2 in an oil field and not have it count as sequestration in Texas, you can do that. You have to get a permit, of course. But if you want it to count as sequestration, you have to go through a process in which the Texas Bureau of Economic Geology, which is a very professional crowd, is able to certify to the state that, in their professional opinion, the sequestration method that's being followed in the oil field will result in not more than 1% of the injected CO2 reaching the atmosphere within 1,000 years. And it's a pretty tight standard. But what the Texas legislation did is it gave the oil producers who used the CO2 it said, basically, if you had a plant that captured more than 70% of its CO2 and delivered that CO2 to an oil producer, and the oil producer injected it and followed the protocol that was prescribed by the Texas Bureau of Economic Geology, the monitoring protocol, verification, mitigation, and so forth, to ensure that that Texas standard was met, then the oil producer got two benefits. The first, they got the severance tax for oil cut in half, which is now worth about $1.50 a barrel, so it's worthwhile to go through the monitoring for them. And secondly, they got a complete exemption on sales tax for any equipment that was used to capture, transport, compress, inject, monitor, and so forth, the CO2. And that's worth a lot in Texas. So Texas did its thing, and we decided, okay, now we'll go back to the federal government. We walked in one day to say, okay, how about second round of loan guarantees? And they said, sorry to tell you, but we gave away all we had in the first round because we just didn't want to consider any more applications. So we were crestfallen, to say the least. And one nice DOE gentleman said, why don't you come over after work tonight? And so we came over to see him after work, and he said, have you thought about applying for a grant instead of a loan? And we said, what's the grant program? He says, it's called the Clean Coal Power Initiative, CCPI 3. And he said, you can't get as much money, but it's a grant and not a loan. And so we checked with our financial advisors, and they said it's better to get someone to give you money than to borrow money from them. So we said, okay, that sounds good. What do we have to do? And so we applied in 2009, and at the very end of 2009, December 2009, DOE told us that we'd been selected for a $350 million grant, which a year later they increased to $450 million. And this same program has had dozens and dozens of technologies and plants, and attempts have been made with it. And now the only ones that are still standing, our project, Mississippi Power is doing an IGCC plant with carbon capture, 65% carbon capture, but no other products. And that plant is going to be in operation before ours is. You're probably familiar with one called Hydrogen Energy of California, or HECA, or HECA, some people say. It's a plant that's moved around California quite a bit looking for a site, but it's proposed here, and it still has a grant from DOE. And there's one post-combustion capture project in Texas of NRGs. Those are the only surviving projects from this huge federal program, which involved many, many billions of dollars. But we have the largest grant, and based on that, we thought, okay, now we have a shot at financing this, because we thought the plant would cost about $2.2 billion in total in the private capital markets, and if we could cut that by $450 million, that gave us a shot at being able to raise the right amount of money. So we had the site, we had the technology, which was Siemens combustion turbine married up with high hydrogen combustion turbine married up with the Siemens gasifiers. And that was the technological heart of the plant, but the commercial heart was that Siemens was willing to guarantee the long-term performance and availability of its combustion turbine operating on syngas from its gasifiers. And at that time, there was no other manufacturer who was willing to do that. General Electric wouldn't do it at that time. They'll do it now. Mitsubishi wouldn't do it at that time. They'll do it now. And consequently, there was no other combination of technology that you could go to the private capital markets and do a project financing for, because you can't project finance a plant unless you can get somebody to guarantee the plant's going to continue to perform. I'm sure you all know that project financing is a species of finance in which, instead of building a plant on your own balance sheet, which in Summit's case would be laughable, you set up a company that's a project company, and people loan money to that company and people invest in that company, but the only source of revenue to pay back the debt and to return a return to the equity investors is whatever money the project can make. In our case, we had to sell the products, and that money had to be sufficient to cover the debt and also return enough to the equity investors to make the equity investors want to invest. And so we needed to have someone who could guarantee that the plant would continue to operate. We ended up with a sometimes it's better to be lucky than to be smart, and we ended up in an interesting situation. The high hydrogen turbine that Siemens was willing to guarantee took them many, many millions of dollars to develop. And they only developed it in one size, which was the so-called F-class combustion turbine. Their gasifiers, on the other hand, as soon as they purchased the gasification technology, they realized the gasification technology could be scaled up quite easily. And so they decided to scale it up to a certain size. And furthermore, to take their gasifiers and package them as so-called twin packs. The result of this was that with 2 gasifiers, we had way too much syngas to operate the 1 combustion turbine, but not nearly enough to operate 2 combustion turbines. So we had to design our power plant to have a combustion turbine and a steam turbine generator so we could combine cycle power plant where you capture the exhaust, the heat from the exhaust of your combustion turbine, you use that to make steam and you use that steam to make power. We had what's called a one-on-one, 1 combustion turbine, 1 steam turbine. And the optimum size for that didn't use, only used about 70% of the syngas. So we had to figure out, okay, what do we do with the rest of the syngas? So we looked at all the different products you could make from the syngas, and we ended up settling on urea as being the best product for fertilizer. The United States is a huge importer of fertilizer. We import about 7 million tons a year out of a 10 million ton demand. Farmers have, I thought we could get a good thing going, let's stop our dependence on foreign fertilizer, but that didn't work. It turned out, of course, that what we learned was something not too surprising, which is of all the products that you can make out of syngas, if you're going to take coal or petcoke and gasify it, of all the products you can make, the least valuable one is electric power, and the most valuable one is probably liquid fuels, diesel, gasoline, whatever. But you can make all of those, that range of things, and we looked at all of them. We decided, let's do urea. So we have an interesting situation for the plant, which is that the plant will use 70% of its syngas to produce electric power, which will produce 22% of the revenues, and it will use 30% to produce urea, which will produce 50+% of the revenues. So it shows you that you're upgrading one of these hydrocarbons, upgrading it to electric power is not your best thing. This is called polygen plant, and everyone started saying how brilliant we were that we had a polygen plant and it had these good revenues and it had exciting returns to the equity investors. That was good. The Permian Basin location. The Permian Basin of West Texas is truly an astonishing place for CO2 because for 40 years, CO2 has been injected in the Permian Basin for oil recovery. It's usually used as what they call tertiary recovery method. You have your primary production, then you do water flooding to push all the water you can. And the CO2 is a solvent, and so when you put it down, it strips the oil off the rocks. About half of it stays down on the first pass, and about half of it comes up with oil. But since you had to compress it to get it to go down, when it comes up, it decompresses, it separates from the oil. You have to recapture it, recompress it, re-inject it, and sort of half stays down each time until ultimately everything you put in is down there. There's a wonderful woman, a geologist at Texas Bureau of Economic Geology, and she gets up and she says, you need to make sure you tell people that from the moment you capture that CO2 and use it for enhanced oil recovery, that CO2 will never encounter the atmosphere. It's always going to go back through that cycle and be stuck in the ground. Of course, the oil has carbon in it. It comes to the surface, and you have more oil production with carbon in it. But the method used is what they call enhanced oil recovery. It's the only method of recovering oil that captures, that leaves CO2 leaves carbon underground. And in the world oil markets, you're not increasing demand or reducing cost or anything else. You're just displacing some oil that's not produced with CO2. So it's a fairly beneficial thing to do. But what's really important is it's happening on a massive scale. The total amount of CO2 injection in the Permian Basin annual, new and recycled, is about 100 million tons a year. So it's massive. And our little plant was going to contribute 2.5 million tons a year, which would be the largest plant in the United States doing that sort of thing. But on the other hand, a very small impact in the total Permian Basin. And we used to think of enhanced oil recovery as being just a bridge to putting sequestration of carbon into saline formations. And for society as a whole and for the globe and for centuries to come, that's really true. It's just a bridge. It's just a bridge when you can't get any other revenue. When no one else will give you money to capture carbon, you can get money from an oil producer, and that's good. Helps you pay to capture the carbon. But it turns out it's a much bigger, wider, longer, deeper, fatter bridge than anybody ever realized. And even in the years we've been working on this project, the total CO2 for EOR potential just in Texas, but then the rest of the country, the rest of the world, it's huge. And so the oil fields, the depleted oil fields, really are a very, very large potential sink, although not nearly as large as the saline formations around the world. So it was a good place, and it turned out there were producers who really wanted to buy the CO2. We were able to sell all the CO2 for 30 years. And we sold it at Permian Basin prices for CO2. All the CO2 they've been using in the Permian Basin is geological CO2. It's all from either domes of CO2 that they find, or it's from gas separation plants. So they find a gas field that's part methane and part CO2, and they separate the two out and use the CO2. So we're the kind of, we think of ourselves as being anthropogenic CO2. And some of the gas separators do as well. The Department of Energy required us to come up with money. So they don't just give you the money, you have to match. They can't pay more than 50% of the cost in any phase. So we had to come up with a bunch of money very quickly. It was stimulus time, and so we couldn't say we're going to do it in a year. We had to do it right away. It was really hard to raise the money. And we were against a DOE deadline, and we ended up, six of us who own our little company ended up having to personally guarantee loans in order to meet DOE's deadline and get the project started in early 2010. So of course, one of the first things you have to do is go through a FEED study. A FEED study means front-end engineering and design study. You have to pay a lot of money. In this case, we paid about $45 million to design the whole plant. And you do that so that the contractors who are going to build the plant can get a good enough idea of what it's going to cost them, how much materials and everything else, how much labor, that they can give you a firm price to build it. And you need to have the firm price in order to go out and finance it. So the FEED occupied 2010, halfway into 2011. Midsummer of 2011, we got the FEED results. All this time we'd been negotiating to sell the power, to sell the CO2, and to sell the urea. We were very fortunate that the city of San Antonio, which is a really progressive city, decided to buy all the electric power from the plant because it's just really low carbon electric power. They had as much wind as they wanted. They were long on gas, and they didn't want any more gas without carbon capture. And so they had a lot of coal. This enabled them to shut down some old coal and have coal with carbon capture. But at the end of the FEED study, the costs of the plant were just too high. The contractors came in, and the cost that they said it was going to cost to build, we couldn't have financed it, and we couldn't have built it. And then we would have joined, another dozen plants or so around the United States that never did get built because they got to that point and the costs were just too high. Why are the costs so high? This is a thing that just drives you crazy because it's the first of a kind plant. And so even though in our plant, all the technology in the plant, every single piece of the technology is in commercial operation somewhere, it's not new, but the integration of it is new. And so when you have to have people guarantee its performance so that you can finance it, they're very, very nervous about guaranteeing the performance of a first plant. And consequently, the costs, they build in a lot to take those risks. The contractors build in a lot of cost to take those risks. So what you're trying to do is make the first plant affordable, have it be built, and then have people's comfort level increase, and then get down to the cost level for the nth plant, which should be a more reasonable one. But this one was a very scary time for us, and so we worked hard, as did the contractors, throughout the end of 2011, to try to get the cost down to a level we could afford. We originally thought the plant was going to cost $2.1 billion, and it would have been well over $3 billion at the prices that we were looking at. So we had to come down. And for the financing of it, we had to make that work, we had to put together three things. One is the government grant, which is great to have. What the government grant allowed us to do was to sell the products at market. So the city of San Antonio didn't pay more for power than they expected to pay for power. The CO2, the oil producers weren't paying any more for CO2 than they did for CO2 that came from a geological dome. The urea producers, the urea buyer was just buying at market. So nobody had to pay extra. One of the things that's doomed these plants in parts of the country is when you have to make the ratepayers pay extra to get the low carbon electric power, and the ratepayers of Illinois say, why should we do it? It's a global problem. Why should we bear that cost? These fights have continually stopped these plants from getting built, but here the government money allowed us to offer all the products at market price instead of at cost, which was good. We still had to get debt in a very large amount, and we started out working with export credit agencies in Germany because so much German content. We had Koreans working on it, so we had the Korean export. We had a bank syndicate. We were going to rating agencies to get project bonds. We were doing all that sort of thing to come up with well over $1 billion of debt to build the plant. And for equity, at the time, we thought we'd need $500 or $600 million of equity. Where would we get it? There wasn't any super premium that the equity investors were going to get because there was no Waxman Markey. But there were some other things. One of the best things that we got was, in addition to our grant, we were able to qualify for special investment tax credits that the federal government had available for projects of this type. And we ended up getting hundreds of millions of dollars of investment tax credits. So when we did our financial model, it looked like we could get good returns. And to attract equity, what kind of returns do you need? You need, for a first-of-a-kind plant, the after-tax returns to the equity have to be in the high 20s, or maybe even the low 30s%. We had people literally say to us, if you can de-risk the projects, there's no risk for me, and I'm assured a 30% after-tax return, then I'll take it to my investment committee. I say, well, thanks, it's hard to do. So here's what we discovered when we went out to finance the plant. First of all, the Polygen plant, the thing that gave us those great returns, all that urea, there's nobody in the world who invests in projects, who invests in a power project, a CO2 project, and a urea project. There are fertilizer companies, there are power companies, there are oil companies, but nobody does all three of those. So nobody had the ability to analyze the plant. We could tell them what the plant was, we could provide all the information, but they didn't have in-house the ability to really think through this project and see how they felt about it as an equity investment. I shouldn't say that nobody did. We got everybody. We always got people saying, I'll put in $150 million, but you need a lead equity investor. We need somebody to be the lead. And that lead party never could really settle on it. We also found out something really interesting, which is for all these tax benefits, nobody had any tax appetite. Tax equity investors had invested in all solar and wind, and they were fully satisfied with that. In the electric power sector and in the natural resources sector, nobody had any tax appetite at all because they all pay alternative minimum tax if they pay any tax. So nobody could use the tax credits. So the only people who could use the tax credits were Google, Microsoft, Apple, and try to even mention the word coal and see how far you get, in the door. Not very far. That was really interesting to us. So in the end, we're now halfway through 2012. We just couldn't put the keystone equity investor into the mix. And we knew we were going to run out of time. So we took the very big step, something we've been working on carefully as an alternative for 2 years. And that was that we went over to China and we sat down with the Chinese and said, okay, the Chinese really, really wanted to have their what's called EPC, engineering, procurement, construction, EPC firms come into the US market and compete with US EPC contractors and also with the Koreans. As it happens, the Chinese are willing to support their EPC contractors with a huge amount of debt. So we ended up getting one loan from the Chinese for the whole amount of debt for the project that we needed. And in addition, they were prepared to make an equity investment to do this as well. So we hired Sinopec Engineering Group to come do the chemical block of the plant. And on that basis, we have finally got it kicked off. We still need about 3% of the money. We figure we're going to get that from someone. Sally has a lot of friends. And we will have the financial closing this summer, and we will start construction. What did we learn? And for the future, this is my last point, so I realize I'm a little bit over here. First of all, this is really hard stuff. It's really, really hard stuff. And it's risky. And it could all end up with nothing, dust in your hands. And it's very, very slow. Not everybody believes that this is an important part of solving the world climate problem, but if you do believe it's an important part of solving the world climate problem, it's going far, far too slowly, globally. But it is possible. That's the important part. What did we want as a little company? We didn't want to become the dominant gasification company in the world. We just wanted people to stop saying it wasn't possible. And what they're going to say is, oh, well, you did it, but you had $450 million from the Department of Energy, and you built yours right in the middle of the Permian Basin with all that oil. And we'll say, but that's a lot different from saying it's not possible. Now you're talking about what terms you can do it under. Believe me, the second plant's going to be so much easier than the first plant. There'll be tremendous savings and lots of other things. I think we believe now, we're believers in CO2 for EOR, and we're prepared to stand up and defend that. Fortunately, most of the national environmental groups are too, but not all of them. And the European environmental groups are not there yet. But understanding that this is a good place to use to capture CO2 and get going on it has been a lot. It's been good for us. We also decided, we can't just do coal. The country's shifting to natural gas, and you've got to do carbon capture for natural gas, and particularly in California. So we actually have a couple projects that are unfortunately not public yet, but we have teamed up with Linde, the big industrial gases company, who has a great post-combustion capture technology for gas, natural gas. And we are going to be doing both a retrofit of an existing natural gas plant and a new build natural gas, or two we hope in California. But the California regulatory regime doesn't really have a place for these. They're not renewables, where do they fit in the whole California scheme? So we're having to work on the whole California policy making. I hope Senator Bingaman will solve this for us. The Chinese is probably the most interesting thing to me. I've been spending an awful lot of time in China. I also have a daughter from China, and it's all been fascinating to me. One thing we know is the Chinese are coming. They're going to be here in force, and it's good. I think there's going to be some really rough transition, but they have this big spigot of money. It's like a fire hose they can't turn off. They've got to point it somewhere. And if they point it to supporting development in the US of things that matter to them, including carbon capture and sequestration, that's actually beneficial all the way around. I'm fascinated in China that the Chinese, they'll tell you, look, to be the top people in this society, you have to be a scientist, an engineer, a mathematician, an engineer. We're all educated. We don't waste any time arguing with our climate scientists. There's nobody in China who denies the climate hypothesis at all. They just say, we do have a lot of other priorities in China. We have, 350 million people with no electricity, and we have to raise up. So it's not our highest priority. And secondly, you people in the West used up all the headroom in the atmosphere, and now, you'd like us to not use up the remainder. Maybe there's a deal to be done here, but it's not as simple as just telling us not to do what you did. And I think that's a fair point. I think this is the beginning. On my best days, I think the Chinese will be using their money to help the United States put its CO2 underground when investing in this project, helping build this project. And that's a good thing, I think, for the world. We found out, for example, that they have not been successful using CO2 for enhanced oil recovery in China. Why not? Well, we had to take them around Texas and show them these things before they said, well, maybe we've been making a mistake. We've been taking 10,000 tons at a time and injecting underground and waiting to see what happened. No. You got millions of tons you have to put in continuously for a really long period of time. Then you're going to see the results, things like this. So there are tremendous lessons from it. I can't tell you today with 100% certainty that we will succeed. I can tell you with 99% certainty we'll succeed. And then let's see what we make of it. We'll see how the country looks at it. But it's very difficult. And so when you think about the geology, when you listen to Sally, when you listen to some of these other people who will come and talk to you, and you're going to have your schedule has some of the great people in this field for the rest of your term. Do appreciate this is not as simple as falling off a log to get one of these things built. It's very, very complex, and we can only hope we're successful. Thank you.
Okay, so we have time for questions, and if we could start off with the students, and then we'll move on if any students, yeah, over there.
You had mentioned, how great your relationship was with the Chinese. Were there any concerns about, technology transfer and possible, some foreign entity stealing your technology?
That's a really good question. In our particular case, there are no concerns at all because I mentioned that we had designed the plant just not to break. It doesn't have any new technology in it. And as it happens, each component already exists in commercial operation in China in many more copies than exist in the West. So for example, we're going to use 2 Siemens gasifiers. I got to go over and see the Chinese, their first installation is 5 Siemens gasifiers all operating They've ordered 30 or 40 more Siemens gasifiers, and now our gasifiers are going to be manufactured in China and shipped to Texas. So it's just an example that they have all the technology. They themselves want to see how it's combined, but there's nothing for them to steal. And also, we're not building anything in China. So, you know, it's the Chinese are coming here, helping us get something that's U.S. jobs, U.S. investment, U.S. oil, et cetera. So I think it's a good story. But it still has to go through the Committee on Foreign Investment in the United States and get approved. That's not done yet.
Okay, how about we'll go over there and then we'll go to the back.
So given that a lot of the investors had maxed out their tax incentives, what do you think is possible in this country to promote financing of these plants?
Well, I think that we shouldn't be trying to do it by tax breaks because people can't take advantage of them. I think that just as we saw with the solar program and the wind program, we had to go to direct grants. If you're going to subsidize it, if you're going to provide government incentives, do it with a grant. The best system is what the UK has devised, which is something they call the contract for differences, where if you capture the carbon, they will guarantee you a price for your electric power that has the carbon removed from it that is the same. So if we do, we're trying to do a plant in the UK as well. And in that, if we have 90% capture there, they will treat 90% of the power as being carbon free. And they're prepared to pay as much as they would pay for wind. And the other 10% they consider to be a dirty old coal plant, and you have to buy allowances for that 10%. But that system enables you to go finance because you now know that the market price risk has been taken away by the government. So that's one way to get it built, which, I mean, I think in the United States we'd have to change all of our programs at a time when Congress can't enact any programs and when I don't think you have a consensus in the country around carbon capture and sequestration that in this field I think we had 5 years ago, but we don't have now. I think we have to get some of these plants built before people start to, develop a consensus around them.
Okay, how about Kareem?
So a couple of quick points. Who paid for the transportation network for the CO2 pipelines?
Oh, the reason we have such a great site is we're sitting right on top of the Permian Basin, which already has 3,000 miles of existing CO2 pipelines. So our connecting pipeline is 1 kilometer long. And Kinder Morgan, which owns the system we're connecting to, is happy to transport other people's CO2 on their pipeline system. So even though it's not as developed as the natural gas pipeline system might be, in the Permian Basin it's sufficiently developed to enable us to do what we're doing, which is this is one reason why the plants in Illinois and Indiana and so forth haven't gotten built, is that in order to get them built, someone has to build a pipeline all the way to Mississippi. And you can't finance the pipeline to Mississippi unless you're sure these capture projects are going to be built. And you can't get those built unless you're sure the pipeline is going to be built. So this dual contingency. And that was probably the most important thing we avoided, was avoiding that dual contingency. All we have to do is get our plant built, which is a big enough problem.
Okay, all right. Okay, how about up here?
You mentioned that you have to, if you're in Texas, you have to guarantee that 99% of your CO2 will remain in those geologic formations for 1,000 years. Is there some danger that with the widespread increase in the use of fracking, more and more of that will escape? That's the first question. Second question is, can you foresee the day 1,000 years later, when this is actually measured, when that can be a good thing, because all release of CO2 will help defray an oncoming ice age?
It's funny. I've made that joke before as a serious joke, which is we now understand enough about climate that we can definitely prevent another ice age. We humans have the ability to do that. But in terms of fracking, the question really was, what about the fracking? Is the fracking going to cause a problem for the CO2 that's put in the oil fields? And the answer is not in the Texas, it won't, because the two oil fields are separated by thousands and thousands of feet of rock. So the oil fields where the CO2 goes are 5,000 feet below the surface, and the fracking is like 10,000 feet below the surface. They're just huge differences. And there's no one fracturing the rock above the oil reservoirs. The oil reservoirs have trapped the oil there for eons, and it's hard to get things out. And the only route really from the oil field for the CO2 to come out is through the wells. So what the monitoring program has to do is first figure out where all those wells are, because not every one, you have to use aerial techniques and all sorts of things, find them, and then check them. But the good news is if CO2 is coming out from a well that you didn't expect, oil is going to be coming out too, and you're going to spot it pretty quickly. And then you have to ensure the integrity of those wells. But how you ensure the integrity of the wells for 1,000 years is an interesting question. One I want to personally be here to make sure that they do a good job on it 1,000 years from now.
Okay, I think that you have one over here.
What's the status of the project, and with all that you've learned, are you going to build more of them?
We're going to try to build more of them, but obviously we're not going to get $450 million from the federal government for the next one, so we have to save $450 million, and that's what we're working on, is to how to optimize the second plant. So we do plan to do another one, but we also plan the one in the United Kingdom. They're good plants to do. The first 5 or 6 should be built in places where 2 things are true. Someone's willing to pay extra to get electric power that doesn't have carbon in it, and someone can use the CO2 for a productive purpose until society starts paying for CO2 capture. And so you have to find basically, you know, the right locations. We foresee about 5 or 6 plants that we want to develop, but I think this carbon capture from natural gas could become a bigger thing. It's got its own challenges, and some of it's not as efficient, but it can be done, and it can be economical, we think.
Okay, we'll go there, and then that'll be the last one.
That's it.
So I know this is a little unfair, but if you had to look into the future and pick a price of carbon that was just high enough to solve a lot of these problems, that would actually incent people to capture the carbon at a coal or natural gas plant and then sequester it, is it $20 a ton, 100, 200, 500? Have you guys taken a look at what would cause the world to really go down the path that we need to go down?
Well, I'm going to respond in 2 ways, neither of which you'll find responsive. The first is that the thing to remember about putting a price on carbon is it doesn't put any money into the hands of people like us who are trying to build a plant. It doesn't contribute $1 towards building the plant. That's really important to remember. What it does is it makes some utility be willing to pay you more for electric power from the plant because you've taken the carbon out. That's it's a very indirect way of getting money into a plant. Very indirect. So we don't go around advocating it for plant building purposes. But I can tell you how I would go about it, and that is any technology that's going to use hydrocarbon, the cost of the capital and operating cost of having it with the carbon capture and without the carbon capture is basically currently 25 to 30% differential. So you could set a price that said, you know, whatever the technology is you're interested in, if it's worth it to utility to make it worth their while to pay 25 to 30% more because they're not having to pay a carbon tax, that would do it. Right now, and it'll get better. I mean, it's going to get cheaper.
Okay, one more. Yes, you.
Where and how far is the coal coming from? What are some specs on coal? Is it bituminous coal you use?
We're using sub-bituminous coal from Wyoming. I mentioned that the site was almost perfect. It has 2 defects. One is that the coal transport is 1,300 miles. That's a long way to bring coal by train. And there's only 1 railroad. That's not good. That's not perfect. The other thing about the site is, believe it or not, in West Texas, the elevation is over 3,000 feet. And if you're building your first plant under perfect conditions, you want to be at sea level because the air is thicker. Your air separation unit is wheezing a little bit at 3,000 feet. So it's not perfect, but it's made up for it by that 1 kilometer pipeline.
Okay, well, thank you so much.
Thanks.